Okay, so sorry for the last moment cancellation of yesterday's lecture. So this week, today I'm taking a live lecture. There will be another live lecture tomorrow, but I'll upload one recorded lecture for yesterday's class. And make sure that you are following all the lectures because from next week your class test will start. The first class test will be on next week and your midsem as well as all the class tests before midsem all the answer script I'll share with you by next Monday. Means today is Tuesday. By next Monday you will receive all the class test as well as midsem answer script. And another important point is you start working on your term paper. I'll not send separate mail. I'll send a mail tomorrow just for the just for collecting the term paper areas that you have chosen, or the or the group members and all. But it is high time to start your term paper from this point. And my last lecture, I think in last week, I have uploaded a lecture on how to select the term papers and all. What are the possible areas, then at least what are the paper currently available with you start understanding from these papers and immediately start your term paper. And if you need any help in selecting areas and all, you can always ask me or Prathamesh. And most probably Prathamesh will also post some important areas, and by today or tomorrow you can also think about those areas for term paper. I think in my last video I have mentioned that you can do your term paper in security issues. Security issues means try to find out the means issues in the existing replacement policies or existing techniques. If you can find out issues, it means somehow if you can degrade the performance of computer using this technique, then also I'll consider those work as good work. And as I have mentioned in my last lecture, I think that it is not necessary that you have to complete the term paper. Means starting proposing, implementing, it's not necessary. What is important is how your proposal is, how good your proposal is. So for this you need to read some papers, which it's not possible to propose a new a good new work by just reading one or two papers. So I'm expecting that today is 15th, so we have more than 1 month remain. So at least you will read ten papers. So one paper per day, or at least if you spend 2 days to understand one paper, then also you can read 10 papers. And after reading 10 papers, you will propose your idea. So already, if you choose any of the areas like replacement policy, 5 6 paper I've already discussed. Partitioning, I've discussed few papers. So and NVM based problem that I have discussed, I have already discussed some paper. Today also I'll discuss a paper on non-volatile memories. So some papers I've already discussed, and now it is your responsibility for the time paper to search some new paper and start exploring it. And yes, during this process, if you face any time, if you feel that I'm not very sure whether to read this paper, or whether I'm not understanding anything, then you can always discuss with me or Prathamesh. So it is from this point, it is your responsibility to continue with your term paper. Yeah, that you have to understand. Okay, so today last class it was based on term paper, and before that I have uploaded lecture on DRAM timing. So DRAM I'll discuss DRAM based main memory, but after a few lectures, means most probably from next week. So before DRAM, there are some more important topics remains from cache memory. And one of the important topic is non-volatile memory. One part of non-volatile memory I have already explained before midsem, but there is some more important point remains. Those will be discussed in this week. And next week I'll discuss another important area of cache memory that's called prefetching. So after completing these two parts, then I'll go to DRAM. Then I'll quickly complete DRAM. This time I'll not cover much areas of DRAM. So the number of lectures on DRAM will be less. And then after DRAM, I'll go to domain specific architectures. Okay, so let me share my screen. I hope my screen is visible. Okay. Okay, so the paper that we'll discuss today is called density. So we'll use this short form density to remember this paper. So before discussing this paper, I will give you some explanation about the concept that is used in this paper. So sorry, this wrong pen. Okay, so if this is your last level cache and this last level cache is made with STT-RAM, suppose, then we know the problem here, right? We know that means uh, just 1 minute. Right. So, so read is same as SRAM and write is expensive, right? We know that write is expensive here in STT RAM based LLC. So if this is your last level cache, okay, designed with STT-RAM, then what are the problems? That these problems are known to us, right? The first problem is uh, the the lifetime of a cell. So if you keep on writing something on a particular cell, then it's this particular cell will be damaged much faster than other cell. So the solution is make the writes uniform throughout the cache, and maintaining uniform writes throughout the last level cache of designed with STT-RAM, the techniques we have already discussed in the class. Some techniques, not all the techniques. Now if you want to do time paper in this area, then you can think about some more techniques on more recent technique and how to uniformly distribute the writes. So now, and today I will not discuss on this topic. Today the will discuss on another problem of STT-RAM, and that is high write latency. The number of writes if write in STT-RAM is also expensive, right? It will take more time, and also it will consume more energy as compared to read, or as compared to SRAM based last level cache. So what normally happens? So every cache has a read write queue. Okay, so assume that this is your request queue. So every core, suppose there are some core here, C1, C2, C3. So all the core has their own L1 cache, suppose. And then if there is a miss in L1 queue, then all this L1 are requesting to this last level cache. So all the requests will first go through this request. So this request queue, this is request queue. Okay, and then this from this request queue one by one, this request will be served. Okay, now the problem here is, if since the number of write takes more time, so suppose there are three writes here, and then there are some requests here, read request here. So what will happen to serve these three writes? Write will take more time, so it means that these it's high chance that if there are number of writes are more, then there will be congestion in the request queue. And if there is a congestion in the request queue, then what will happen? The performance will degrade, because the suppose maximum writes are requesting by this code, and they are just requesting for read. But since the cache is congested, the last level cache is congested, or you can say the request queue is congested, then what will happen? Then this C2 and C3 will get response late. Why? Because the queue is congested. So what will happen ultimately, that the performance of C2 and the application that is running on C2 and C3 will also degrade. So so this is the problem. It's not it's not just related with last level case, it's related with the other core also. May because we may think in this way that okay, only the application that is running on C1 is going for multiple writes, and the write is expensive in last level cache. Assume last level cache is with non-volatile memory only. So the write is expensive in non-volatile in last level cache, so only the performance of application that is running here, that is A1, will be affected. But that is not true. The performance of A2 and A3 will also get affected because of the congestion, because write will take more time and it will congest the request queue. So this is the problem. So how to solve this problem? This One of the solution to solve this problem is, uh, uh, what if we bypass some of the rights? Bypass means, to understand the right bypassing, we have to go to main memory also. So suppose we have a main memory here, and now suppose this core is requesting, C1 is requesting for three write, W1, W2, W3. It is going for three writes. Okay. Consider that these writes are coming out of L1, means L1 is full. Suppose L1 is full and W1, W, these are the blocks we need to write back to last level cache. Now, so all this W1, W2 and W, there are three blocks. Instead of writing these three blocks, if we can find that, okay, out of this block W3 is not live. It's not live means it will not going to re-access again by in near future by any core. Means if W3 will be written here, then in near future no other core will send a read request to this W3. So if the no other core will send a read request in near future, then it is not necessary. It is not important to store it in LLC, right? So in that case, what they will do, they will simply bypass the last level cache, and they will simply write it in the main memory. This is called write bypassing. If you do write bypassing, then what will happen? Then this block will not be written in LLC. Okay. So the write bypassing technique is not direct, means it's independent from STTRM. It's not like that the concept of write bypassing only comes after STTRM, or after people facing the STTRM issue in LLC. It's not like this. Write bypassing concept were there when the LLC was designed with SRAM also. So suppose that if the LLC is designed with SRAM, not STTRM, then how the write bypassing will help? So just for a moment, if you assume that the last level case is designed with SRAM, where read and write are of same cost, so their write is not expensive. In that case also, if suppose at that time, if C1 is requesting multiple writes, and in that case, if you face that, okay, there is some write that is W3, is it will not repeat again in near future, then it's better to bypass, right? If we bypass this, then what will happen? We no need to waste a space here in last level cache for W3, because if you write W3 here, then it will waste a particular space, right? Unnecessary, it will be placed here like a dead block. So if we know that this block is dead, or if this block will not be requested in near future, then directly write it to the main memory, such that there will be space available here. And if there is a space available here, then what will happen? It will increase the hit rate, right? The write bypassing technique was already there from SRAM based LLC, and that time it was only used to increase the hit rate. Okay, but here in STTRAM based LLC, you will understand that it is not important to increase hit rate, even if sometime if we do some more so okay, one more point here. So when we do write bypassing on SRAM, as I said, in SRAM based LLC, we do write bypassing only to increase the hit rate. So it means that the bypassing must be restricted. If we go for more bypassing, and if somehow we bypass some important writes, suppose W1 and W2, suppose these two are important blocks, and in near future some core will request for them, but we have bypassed them. If we bypass them, what will happen? When the core in future, when the core will request for this block, then there will be miss. So we have to think that by write bypassing, our main goal is to increase the hit rate. Should not be the goal should not be decreasing the hit rate. So if you go for more aggressive writes in SRAM based LLC, it may be possible that the goal that you want to achieve, that hit rate, that will not achieve, or it will do the reverse thing. It will ultimately decrease the hit rate. So that should be a balance. So there are different works based on that. I'll not discuss all the work here, but when we'll go with STTRAM here, even sometime if you go for aggressive bypassing, and by aggressive bypassing, even if you think that the hit rate of LLC is decreasing somehow, then also it may be benefited. It may give benefit. So this point is very important for NBM, because if we go for NBM LLC, we can go for aggressive bypassing. Why aggressive bypassing? Because if you go for aggressive bypassing, then maybe the hit rate will decrease in LLC. That is same here. But even after decreasing hit rate, I'm saying it may be possible that there are some performance gain. Why? Because of the congestion. Because if we bypass more rights to LLC, then what will happen? The LLC will be free for serving the read request, more read request of other core. And in that case, even if there are some reduction in hit rate, and also it will perform the improve the performance. So this is the very important point here, and this is the technical difference between the STT-RAM based LLC and SRAM based LLC. This is one of the very important difference, and this important difference is means it's considered as a motivation for the paper that I will discuss today. Okay, so any other important point? Uh, Okay. Before starting the paper, one more important point I'll discuss. So here I said more aggressive bypassing is possible if it is an STDRAM based LLC. So we can bypass more number of writes. But even if you go for aggressive bypassing, but still there should be a point. Here also, as I said, if the heat rate decrease, even the heat rate decrease, then also there is a chance to improve performance. But it's not like that you will decrease heat rate by 90% and expected that the performance will improve. It's not like this, right? That should be a threshold for everything. You should decrease hit rate in up to a certain level, and up to that level it should increase. It will give the benefit. If you decrease the hit rate more, then it will not give benefit. So if you think that no, I'll bypass all the rights, then it will not give benefit, obviously, because if you bypass all the rights, then even if your read request is not congested, you may underuse the last level cache. So there should be a balance between all these things. So based on this concept, there's a very interesting paper that I will discuss today. Is called density. So you can see this paper is published in ISCA 2018. So it's a very good paper, but unfortunately, when I read this paper, the concept is very interesting, but the writing style is not very good. Sometimes we need to read a few section multiple times to understand. So writing style could have been improved, but we'll ignore the writing style here. Why? Because the idea is very interesting. So if you start from introduction section, they have explained the concept that I have already discussed here. If you read this section, they have explained the point that what is write bypassing and how write bypassing was there in SRAM cache, and why more aggressive write bypassing is required for NBM. All these things they discussed. Then since the more aggressive write bypassing is required in NBM based NBM, though they have written NVM, we are considering here it STT-RAM, right? So STT-RAM and NVM, you have to consider the same thing here. So if there is a STT-RAM based LLC, then how we can propose new write bypassing technique which is more aggressive. All these things they have explained here. So I'll advise you to read the complete introduction section, even this point. So this is their main proposal. The first point is their main proposal of this paper. So they have proposed a smart bypassing technique for NBM based or STT-RAM based LLC, such that it should improve the performance. It should reduce the congestion of read queue, and as well as it should improve the performance. So the write bypassing technique they use is more aggressive than the existing write bypassing technique, as well as is also considered that it should not degrade the performance, because our main intention here is to improve the performance. And also there is a secondary goal is the reduce the energy consumption of LLC. How we can reduce the energy consumption of LLC? Because the rides are expensive in LLC, right? For STDRAM LLC. So if you can reduce the number of rides in LLC, then obviously latency will improve. That is the first primary goal. Secondary goal, it will also improve the energy consumption of last level cache. Okay, so then here the last 2 points they have just explained their experimental details. Okay, and then background and motivation, I'll advise you to read this section once, but I hope all the concept written in this section, background and motivation section, you will understand it, because pre-midsem I have already explained the concept of STDRAM. Okay, so write versus cache latency, this point is very interesting, and you in this section you'll find some interesting results. Interesting results means when we have discussed SRAM, if you remember, we mentioned that as sorry, not SRAM, STDRAM, that STDRAM has high density as compared to SRAM. So density means if in suppose this is the cache space chip space area. So If you go for SRAM, and if you can place here 4 MB of SRAM cache, then maybe if you go with STD-RAM, then at least you can place, I think, 8 MB of STD-RAM. This is possible because the density of STD-RAM is high. If you go with DRAM, I hope this part I have explained, then in the same cache space you can store more, at least I think 24 MB of DRAM is possible, and even maybe even more. So density of this non-volatile memory as well as DRAM is more than SRAM. Okay, so it means that if you have designed a chip, and as a designer you left this much area or inside the chip for a cache memory, for the last level cache memory, then if you go with SRAM, then you can store use a 4 MB memory here. But if you go with NBM, it may be more than 8 MB, but here I'm assuming that you can easily go with the 8 MB of non-volatile memory, because it is high density. Non-volatile memory, non-volatile memory is high density. But now the question is, area wise, okay, STD-RAM is good, that is fine, but the next question is, even after going with 8 MB LLC, which one will give best performance? Suppose this is design 1 and design 2. Which design will give best performance? Even if we go for 8 MB LLC instead of 4 MB SRAM, but even after going with design D2, if the performance is less than the design of D1, then there is no point of going with a bigger size cache, right? Why I'm saying this? If you go to this paper here, just see the first figure here. In first figure, they have compared different SRAM last level cache, SRAM cache with 4 MB, SRAM cache with 8 MB, SRAM cache with 16 MB. These are the last level cache size, and this is the normalized to, I think this is the performance. This side is performance, higher is better. So you can see the performance of 4 MB is 1. So performance of 8 MB is 15% better. Performance of 16 MB SRAM is 23% better than the 4 MB SRAM. So the performance is increasing. If we concentrate on SRAM based last level cache, if you simply increase the size of the cache, it is improving the performance. Why it is improving the performance? Because it is increasing the hit rate, right? The number of misses will be reduced because of using larger size last level cache. But the second figure is very interesting. If you consider in second figure what they are comparing here, that the first one is the first, this one I'll write it as 1. So this one is actually a 4 MB SRAM LLC, okay, and the second one is actually a 8 this one 2 3 4 5. This 2 3 4 5 are STT RAM based LLC. So first one is a 4 MB SRAM LLC, and the 2 3 4 5 are actually 8 MB STT RAM LLC. And how they are different? You can see in two, it is STT RAM, but a write latency is same as SRAM. That's why it can hear plus 0 nanosecond. The second one is write latency is 5 nanosecond extra of SRAM. Third one is write latency is 10 nanosecond extra of SRAM. And the fifth one is the write latency is 20 nanosecond more than SRAM, which is actually the normal case, right? When we go for STT-RAM, then the write latency of STT-RAM will be at least 20 nanosecond more than SRAM. So you can see the difference. All three, 2, 3, 4, 5, all are actually 8 MB of LLC designed with STD-RAM. But you can see the performance. When we can use the 8 MB SRAM, STD-RAM with the same write latency as the SRAM, then you can see the performance is improving by 15%, which is true here, right? It is true in both cases. It is improving 15%. But if you increase the write latency, which is normally correct, right? Because the write latency will be more. Since it is a simulator, the results are taken from simulator, then you can easily change the write latency of STD-RAM also. So first time they, in first design, they consider that write latency is same as SRAM. So you can see that 15% performance gain. But if you skip increasing the write latency, then you can see the performance is degrading. And if you see the last one, that is the experiment number 5, you can see here. Here we assume that the write latency is 20 nanosecond more than SRAM. And in that case, you can see that even after if you go with the 8 MB SRAM cache, the performance is degrading compared to a 4 MB SRAM cache. So if you go to my design here, this is the design D1 and D2, and the write in STRAM is 20 nanosecond 20 nanosecond more than SRAM. If this is the case, then this D2, even after it is going with 8 MB LLC, it is degrading the performance by 15%, right? If we go here, it is 0.8. So it is degrading the performance by 15% as compared to a 4 MB SRAM, not a 8 MB SRAM. So you can see from this motivational figure, you can see that there is a lot of performance gap exists, because even if we are going with larger sizes non-volatile memories, there is a performance gaps, and we need to do something to improve the performance. So these two graphs are motivational graph, and these two graphs you can it's not just for write bypassing or something. This graph said that there are a lot of work is possible in this area. The same way when we have discussed replacement policy, what we said that in there is a huge gap between the Belard's optimal replacement policy and the replacement policy that are currently exist. That there is a huge gap still exists. So that it represents that there are more research possible in replacement policies to reduce the gap. The same thing here, you can see there is a huge gap between the performance of a SRAM based LLC and a an NVM based LLC. So you can there is a lot of work possible in this area to reduce the gap. Okay, so that you have to this is given in written in this motivational section. And then they have written something called sources of right NLC. Yeah, I personally feel that the section subsection B and subsection C are not properly means the flow is not matching here, but whatever content written here is very interesting. So whatever content written here, to understand this content, I think what they written, most probably they've written here for exclusive, yeah, exclusive and inclusive. So I'll use my own example here to explain you this point. uh, yeah, so suppose I'll go with this single code setup. So we have two suppose L2 is my last level cache. I'll not write main memory, or let us discuss main memory here also. This is main memory, core is here suppose. So this is my processor. So what is inclusive cache and what is exclusive cache? Inclusive cache means whatever data present in this L1, a copy of this data will be also present in L2, right? So you can say the L2 is the big brother. Whatever data contained in L1 is also available in L2. So it means that whenever there is a request for a block, the block will be first fetched from main memory to L2, and the block will be placed here, and then if required, then the copy of this block will be sent here also. So you can say that the content or the data available in L2 or the block available in L2 is a superset of the block available in L1. This is called inclusive cache. Okay. And exclusive cache means whatever data available in L1 will not be included in L2. So if suppose this is the this is the current scenario, and now at this moment if C1 request for a block B, then obviously there will be miss in L1. So the request will go to L2, and from L2 the block will be given to L1. Okay, and the block will be removed from L2. So what is the advantage here? So obviously there will be no A also. What is the advantage here? The advantage here is you can use the cache space in more better way. So it can reduce the number of misses. Why? Because we need the copy at least if we can make sure that okay, at least one of the cache, because L1, L2 all are on chip memories. If any of the on chip memory has a copy of this block, then we can remove it from other place. Maybe managing it, maintaining coherence will be difficult, but that is not the point here. The point is possible or not. Yes, it is possible. And if you do this, then the positive side here is you can use more cache space. It may reduce the hit rate. Obviously it has some other issues are like how to handle coherence and all, but I'll not discuss here all this point. But the another challenge here is, since this is exclusive cache, so what we normally do in inclusive cache, again I'm going back to inclusive cache now. I'm again explaining inclusive. I'll come back to exclusive after some time. So if it is a exclusive cache, then means A, B both will be here, right? This is exclusive cache. So now just concentrate on L1. Out of A, B, assume that this block B is dirty. Dirty means the code has written something to this block. So now when both A and B, suppose first when A will be need to be evicted from L1, when we'll go for eviction? If we go with the right back policy, then we'll evict it when L1 is full. If L1 is full, then one by one we have to evict the block. So suppose A need to be evicted. If the A is not dirty, then we no need to write it back to L2. We'll simply just remove it from A. That's it, right? So A will be removed. But if we want to remove B, then you cannot silently remove, right? Because it's a dirty block. So before silently removing, we will write the copy back here B, such that the value of B here will be updated, right? And then we can delete it from L1. This is how we maintain it for inclusive cache. Now I am going again with exclusive cache. Situation is like this: A, B, and the blocks are not in L2. In this case, if we remove A from here, do you think that we can silently remove? If we silently remove it, then it will go from vanished from the cache, and that is not the policy, right? Because we are using a larger size L2, larger size cache here to store more data in the cache. If there is a miss from if the block is removed from L1, and if we simply remove it from the cache, then the main property of cache, there is a principle of locality, will not get benefit as per the principle of locality. So in that case, what you need to do, no matter it's a dirty block or a clean block, if you are removing it from LLC, from L1, if you want to remove A from L1, then we have to write it back here. That you have to understand here, that if you go with exclusive class, then cache, then this is the disadvantage. Obviously there are advantage of exclusive cache, but this you have to do. So you need to go for removing B, then you have to write it B here. It is not necessary to check that if it is dirty or not, you have to write it back. Okay, so now I hope you're understanding the limitation of inclusive and exclusive cache. Now coming back with STT-RAM based LLC, if we go with STT-RAM based LLC, can you understand? Can you comment here that which will be more expensive, inclusive cache or exclusive cache? Anyone? I've explained you the concept of inclusive and exclusive. Now, can you comment that which one will be more expensive if we go with STT-RAM based LLC? No one? No idea?
Inclusive.
Why inclusive? Why inclusive will be more expensive? Yeah, Upasana is saying exclusive due to high write latency. Anyone else? Can you verify what Upasana is saying? Do you think Upasana is correct?
Yes, sir. Yes.
Why?
Sir, same reason. The writes we need to, as you have said, that we need to write to L2 catch also. So, and the write latency will be more, right? So, I
Yeah.
think, yeah.
Yes, correct. This is the correct answer. Why exclusive will be expensive? Because here we need, in case of exclusive, we need to go with some unnecessary write, because every time we're evicting from L1, we have to write it back in L2. So I think if we go with exclusive design, then it is more important to think about the whether you should go with STDRAM LLC or not. And if your underlying replacement policy, underlying design here is underlying LLC design with STDRAM, then we need to take more care. If it is exclusive cache, then how you can design STDRAM in such a way that it can handle writes. So this is again a big area of research. So honestly, this paper, though they have discussed this concept here, so their work is not directly related with exclusive cache. Their work is related with just NVM based LLC, that how to reduce the number of writes in LLC. So it will work for both inclusive and exclusive. But this is a very interesting section they have discussed here. Now there is a related work section, and what I'll do here, I'll advise you to read the related work section once and try to understand these papers lab. Though these papers, just you remember here, this paper will not be considered as in syllabus of your NSEM exam, but maybe this paper will give you some idea about your term paper, about further research. So the paper, right, LAP, and I think there are two more papers here. I think uh, I think 12 and 5, I think. I'll explain it later when they have mentioned. I think they have mentioned it here, that they've used this concept of 12 and 5. See, 5 and 12. You can read these two papers also. These two papers are basically mainly based on detecting dead block from the cache memories. Okay, for now, if I scroll this paper, so related work, you can just read it once, and then the actual proposal is starting from here. Proposed LLC architecture. So what they did to go for right bypass, so they call their technique as right congestion aware bypass, or WCAP. Okay, so this is their technique, but still will you remember this paper as density paper. Okay, so now you can see that for a particular core, if you see the figure here, that they can see that for a particular benchmark here, you can see that if this is the interval, so at some time you have very high request queue. This request queue is very congested, or the core is giving high request. This is in each circle, it's a combination of read and write both. Red are actually a number of writes, and black, so you can see a number of writes and number of read, both are here. So you can see there are in some time there will be more request in the request queue, and in some time the request queue can be ideal also, right? So when there is a more request in the request queue, if you don't balance it properly, then what will happen, there will be a congestion in request queue if it is a NBM based LLC. So now you can see there are two more interesting results here, figure 4 and figure 5. Figure 4, this is figure 4 and this is figure 5. So let us first discuss figure 4. If you go with figure 4, you can see this is a SRAM based design. So in SRAM based design, if you keep on increasing the right bypassing aggressiveness, 0% means no right bypassing, 10% right bypassing, 20% right bypassing. So this is the aggressiveness of right bypassing. So if you increase the aggressiveness of right bypassing, then what is happening here, if it is a STTM based design, it is simply degrading the performance. You can see it is degrading the performance if you go with more right bypass, more aggressive right bypass, because it is not able to increase the performance, because write and read are same in SRAM, and if you decrease this, then what will happen, it is decreasing the hit rate. It is not increasing the hit rate. Though as at the beginning of today's lecture I said there are some smart right bypassing techniques exist for even SRAM design also to increase the hit rate, but here they have used, I think, simple right bypassing, not any existing smart bypassing technique. So if you increase the aggressiveness of bypassing, what is happening, you can say the performance of all the applications are degrading. But let us go and check the figure 5, and figure 5 is for STT-RAM based LLC. In STT-RAM based LLC, if you increase the bypassing aggressiveness, you can see some of the application initially they are giving an improvement, right? And after giving improvement, they are decreasing. Though there are some application like this application, it is decreasing from the beginning only. So I'll discuss it later. This application, see, this is decreasing from the beginning, but it is happen, you can see that for most of the application, if you increase the bypass aggressiveness of right bypassing, initially it is giving some benefit in these areas, right? So and after it will decrease. So what does it mean? It means that in if the last level cache is designed with STT-RAM, then we can increase the aggressiveness up certain limit. If we increase it up to a certain limit, then it will give you benefit. For example, here you can see there is a benefit at this point, but after this certain limit we have to find out up to which limit, and after that we have to stop bypassing, because after that again the STT-RAM will also degrade the performance. So the main point of this paper is how to right bypass up to this point such that it can improve the performance, and after this it should stop bypassing. Okay, so now what about the this the last one here? As I said, this, if you see the last benchmark here, this benchmark is not giving improvement even if you go for right bypassing. Why? The reason maybe here is the most of the right that it is requesting, almost suppose the core is requesting for multiple rights here, then all the rights may be important. Rights may be important means all the rights may be after some time, within a very short period, another core is requesting for them, requesting to read this block. So all the we can consider that all W1, W2, W3 has high liveness here. By the term liveness, I'm saying that if a core is requesting a block in LLC, how likely that in near future another core will send a read request for this. Write request is not important here, because write means you are overwriting something. But if you are writing a block, suppose W3 here in LLC, and in near future if another block is sending a read request to this, then this block is important to be present in LLC. Otherwise there will be miss, right? So if there is liveness is more, then it is better to store those block in the cache. Otherwise, if suppose W2, W3, W1, W2, W3, all this block when we are writing, if their liveness is high, it means they're highly likely that in near future some core will send a read request for them. So it's better to store them in LLC. So it may be the case that for this application, which is not giving any improvement for increasing the write bypassing, it may be possible then the behavior of the application in such a way that most of the write that is doing in the LLC have the high liveness value. And because of that, if we are bypassing those writes, then next time it is facing a miss in the last level cache, and that's why it is degrading the performance. But overall, so when we design, when we propose some policy, it has to take care about all the situation, right? It should take care about this spike point, that is fine, but at the same time it should also take care about the application that will not get benefit from it. And this paper density is doing this. They are combining all these and they are proposing a technique, so it should work efficiently. Okay, so for this there are two important points they consider. First is liveness. Liveness means they will keep on bypassing until before bypassing, suppose this is the read queue, and the read queue there are multiple write exists, then which write will bypass? Means suppose this two has low liveness value, so it is better to bypass this two. And if this two W has a high liveness value, then it's better to keep this two block in LLC, not no need to bypass. So they handle it. So now before that, the first point that I'll discuss here is when they will bypass. So they will bypass it, bypass the block. Suppose this is the queue, this is the request queue. So if the request queue is full or request queue is congested, and the number of writes here, suppose number of writes here, there are two read requests and four write requests, suppose. So the first condition that when the bypass should trigger, the bypass should trigger when the request queue is congested. This is the first point, and the number of writes request in this request queue is more than a threshold. So that threshold they say it as write th. They have to understand it, that if the number of writes in a queue is more than the threshold, then only writes the write bypassing should trigger. And at the same time, the request queue should be also full. It's not like that the request queue is not congested, like these two places are empty, and but the number of writes is more than write threshold, then go for write bypassing. Then they said no. If both situations should be there, that if request queue is congested plus the number of write is more than the threshold that as mentioned here, then go for write bypassing. Now after this so here they have just said when to start write bypassing, right? This is the means this is the triggering point. So if this condition is true, then start write bypassing. That is true. The next question is how much write bypassing, means if from this queue whether it should go for one write bypass, two write bypass, how much write bypassing, and if we just start write bypassing, up to which point we should continue about write bypassing. It's not like that we should bypass everything, right? So for that they use one more interval, say interval write occurrence. So because there's measure multiple windows, these are k intervals. Suppose it is interval of how many cycles? 100 cycles, 100 kilocycles. So in every cycle in this cycle they'll assume that okay, what was the average number of write and what was the average occupancy. In the same cycle here, what are the average number of writes and number of writes and occupancy. Number of writes and occupancy, number of writes and occupancy, they'll collect from different windows, and then they'll find out the average, means average number of writes in last k window and average number of occupancy in last k window. They will store it, and based on this they will decide something. So I'll go to the diagram and I'll explain it from here. Okay, when to start, suppose this is your queue, and this queue has read, write, request both. So if there is any request, read or write, arrives at LLC, so this is your LLC. Okay, so if there is any read, write request arrive, first they will check that if so they give read more preference. So you can see if any read is ready, then they will send read. So if they are giving read more preference, and if there is no read ready, then they will send a write. So if we suppose this is right now, this right, this is the time, so to solve this right. So to solve this right, there are 2 points. First, we'll write it here, or second is we'll bypass it here and will not write it here. So either we'll go to right or bypass this. This will be decided by the this flowchart that is showing here. So how they have decided? First point, they are checking the threshold. If the request queue is full, if this queue is full, and if the number of write is more than threshold, as I said, if this is the triggering point. If this is not true, then no bypass, done. Okay, but if this is true, then we should go for bypass. Once we start that, okay, bypass, then how much bypass? First here they will take this interval occurrence, means interval write occurrence. As I said, they take the this average of multiple windows. Okay, so if you, these two step here is actually mentioned in this table. So first they will find out this interval right occupancy. If the interval right occupancy is 1/4 of the request queue, it may be half of the request queue, 3/4 of the request queue, and equal to the request queue. This is the average right occupancy of multiple previous k windows. Okay, so if the number of writes is 1/4 of the request queue, then 20% write back, means you will go with 20% number of 20% write bypassing. If the half of the request queue is full with write, then we'll go with 50% write bypassing. If 3/4 of the request queue is full with write, then we'll go for 70% write bypassing. And if the full queue is the number of write is equal to the request queue, then we'll go for 100% write bypassing. So these are the technique, and you can see write threshold they have used as 70% request here. Okay, so now the next question is how they're performing it. Okay, so one more question left is, okay, we find out that this is the request queue and number of writes, that there are many number of writes exist here, that is fine. And now it is also saying that go with 50% write bypassing. So out of all, suppose there are six here, so I should go for there are six writes, so out of this six write will go for three right bypassing. But still the next question is which three? There are six right? Out of these six, which three should be the better candidate for right bypassing? So that is deciding here, I think, in this point. That, as I said at the beginning, there is a point I said about live score, right? Live score. So out of these three, who's the minimum live score? Suppose here the live score is 3, 3, 2, 2, and maybe 1, 1. So these are high live score, means there is high chance that these blocks will be. Suppose this is also this is 1. Suppose so these three, the last three, have high chance that they will be re-access requested again because of high live score. So better this will not, let us write this in LLC, so we'll bypass this two, 1 1 1. So that's why they are going with minimum live score, you can say. So once it is decided that how much block need to be evicted, that will decide it here in these 2 points. And once this is decided, then which block to be evicted? The block having low live score. So the block having low live score will be bypassed here. You can see they are bypassing the low live score here. And after this policy will keep on repeating. So I hope you understand this point. The one point that I have not explained here is how to calculate the live score. This is the next important point. So I'll quickly explain it, how to calculate the live score. So here you have to understand, as I said, that there will be a core and there will be L1 cache. Suppose in this cache, I think they have assumed L1 and L2 as private. Okay, and then there is the LLC here. Suppose this is the last level cache, and this is the queue of last level cache, right, that I have said. So what they are saying here, that every block that is stored in L2, there is a liveness counter is also exist with this. So a liveness value will be exist here. So if, I think better to design it here, otherwise you'll get confused. So suppose this is your L1, this is L2. So every block that is placed in L2, there is a liveness value also exists to this. Suppose A, with this there will be a liveness value of 1. Suppose B, there will be a liveness value, suppose 3. All these things are there in L2 cache. And when there will be eviction from B2, when there is a write is required from L2, then this block B will all come with its liveness value here in LLC. This is LLC, suppose, okay, or L3. So the queue here, in this queue, when this request will be inserted, it will also insert along with its liveness counter. And this way the liveness counter value is available in LLC. But the next question is how in L2 the liveness counters are inserted. So in L2 there are some prediction table, and based on this prediction table they are calculating the liveness. And this liveness value is every time there is, when there is an insertion in L2, there will be two table here, prediction table. Based on these two prediction table, they predict the liveness, and that liveness value they are inserting along with the block. And this concept is explained, I think, here. Learning cost of bypass. So if you go here, this section, they've explained it. So the idea, since I have less time, I think 5-6 minute time is left, I'll try to explain the concept within 5-6 minutes. So what they are doing, they are again using the concept on of sample set. Yes, the sample set concept is used in UCP based partitioning, then dynamic replacement policy, then RRIP, DRRIP. And then again, I think in Hawkeye also there is a concept of sample set. That's why if you remember, when I was explaining the DIP, dynamic insertion policy, I said the concept of dynamic set sampling will be used even in modern replacement, modern paper also. So you can see DIP was proposed in 2007, I think, and Hawkeye is 2017, density is 2018. Still people are using this concept of sample set. Okay, so what they do, they use a uh, table like this. This is a prediction table, and this is indexed with program counter. PC based hashing is there, and for each program counter they use four buckets here. Okay, this bucket is for suppose 20%, then it is for, I think, 50, then it is then 70, and then is 100%. So 20% bucket means the all the blocks from this program counter that are written in LLC, out of them 20% are again requested. So 50% means all the block from this program counter which are writing in the LLC, out of them 50% are again requesting, 70%, 100% like this. So you can see there are different liveness counters. So if you remember the liveness counter, I said, so here they are using four liveness counter here. One is, suppose it is 0, 1, 2, 3. Okay, so 100% liveness means almost all the 100% means here the bucket is actually like this: 0 to 20, 21 to 50, 51 to 70, and 71 to 100. So in last bucket means that if the liveness is 3, means that the most of the block that is writing from this program counter in the LLC is again reading by another processor or another core or the same core. So there will be a hit again for that block. So why they are indexing with the program counter? This is the same concept like what you can say Hawkeye. So program counter means we know that if we go for assembly language, then there are load store instruction which are actually communicating with memory, right? So each of these instruction has a program counter. So they are indexing with this program counter. Okay, for this program counter, which blocks are writing, and for this program counter again, when this program counter will revisit, then what are the chances that this block will be read again. Okay, so this type of and they are observing this behavior, this table only for sample set, not for all set. So they are also maintaining another table here which will store the partial tag of all the blocks of sample set. So if there is suppose this is your L2, so they are doing all these thing in L2. So this is your L2 cache. So if there is a miss in if there is a eviction from the L2 cache, then the partial tag of that block will be stored in this table. Okay, and again if that block will be a hit in the LLC, then they will find out that okay, this block is hit in the LLC. So based on this they will increment this counter. So I'm not explaining this point in more detail because I don't have time, but I hope you will understand this section. See, it is starting from here, learning the cost of bypass. You will understand this section here. There are two tables they maintain. This is the prediction table, and at the same as well as they'll also maintain a table with partial tag. Okay, and if you are not understanding this the concept that I've discussed, that they have discussed here, as I said, it's true that their writing style is not good. Everything is not written clearly. If you are not understanding the concept from here, then I advise you to read these two paper, because they say the concept they are using here is from 5 and 12. So based on this, they are using the liveness. They are storing the liveness. So you read this paper. This is important. And after this, I have explained right bypassing. After right bypassing, they are doing two more important things. This is called virtual hybrid cache concept. So I am not explaining the concept of virtual hybrid cache here. I hope you will easily understand it. So the important point is still here. You have to understand till this point. Even if you not follow the evaluation methodology, that is fine. But exam purpose, you have to read this till this point. Important point I've already explained. Okay, but in if you think about term paper, you can also think way. One is how to improve this area. For your information, Prathamesh did his MTech work on this. His MTP was how to improve the this density paper. He has found some limitation in density, and his proposal was based on this, how to improve the performance. So one way you can simply go with, you can read some more paper, and you can go with how to design better right bypassing technique. This is one way. Another technique that I say, think about the security angle. Is it possible to fool this policy of density? I'll give you idea, because there are some predicted set already there, right? They are using some sample set. If you can do something in such a way that you can give a behavior like this, that okay, you can do something like this, that you can improve the liveness of all the writes, suppose. So what will happen, that when the queue is full in LLC, and if you want to write something, bypass some write, you will find the liveness of all the blocks are high. If this is the case, then you can bypass only less number of writes, and again there will be congestion. So you can think in this direction also, that is it possible to fool this technique, and can you use the misuse the concept that is explained in this section of prediction and all, and you can give more liveness value to a particular block, or if you get less liveness value to a particular block, and either you can increase the number of means, right, or in LLC, or you can underperform the LLC. So both this type of concept is this you can think about these areas. So there is always a security issues, and you can think in this direction also. Okay, so I'll stop here, and if you have any question, you can ask me now. And don't forget to start your term paper as soon as possible. So I'll not send any separate alert for you, but I'll send a mail just for your term paper group and the area of the term paper. So start immediately working on your stamp paper. If you need any paper, anything, then you can discuss with me and Prathamesh both. But this is the high time to start your term paper. At the end of this month, I'll take a small presentation from your side, that how much you have done in your term paper. So I'll expect you that you'll read some more papers. Don't think much. When you start research, term paper is part of research, right? So initially you just try to understand, read more papers. So at least I'll expect that in next 2 weeks, that is today is 15, you will read at least 7 8 new papers. You search it. If you feel that if you don't feel confident that whether this paper is good or bad, then you can discuss with me and Prathamesh.
Hello.
Hello, simple.
Sir, can you please explain why exclusive cache have high write latency in case of STT-RAM?
Okay. So anyone here who has a class from 10? If you have class from 10, you can leave. Otherwise, I'll take 5 minutes more to explain this concept. Okay. If you have class, then you can leave. So what I was saying is, just let us try to understand the inclusive cache and exclusive cache. Forgot about the STT-RAM. This is this is my main memory. So first, inclusive cache means if there is a request for a block, suppose A, so block is not in L1, block request will be in L2, block is not in L2, request will go to main memory, and from main memory, suppose block is given to the processor. This is my chip. Okay, so first time, sorry, not B, this is A. Okay. So I'll place the block here in L2, and then I'll send the block here in L1. Okay, so this is called inclusive cache. This is called inclusive cache, means whatever block that is present in L1, it is also present in L2. This is called exclusive cache. So if there are block like A, B, C, D, E, there are multiple blocks present in L2, then out of this, maybe suppose A and D are present in L1. This is inclusive case, means whatever block present in L1 is also present in L2. So this is the case. Okay, now suppose in this L1, this D is dirty block. Dirty means C1 has written something to this block. So it means that this block is updated block. And it means that the block, the current value of D that is available in L2, this is not updated. Or you can say this is a stale copy. Stale copy means old copy. So I hope when I was explaining coherence, I've explained all these things, right? How to maintain it. So for this, you need modification permission, share state, M state, all I have already explained. So I'm ignoring all these things. So in this point, the D is a stale copy. So when the L1, the core will request for a new block. Suppose the core is now request for a block called E. So in L1, suppose there is no space for E. So you have to remove a block. So assume that the replacement policy selected D to remove. So in that case, you cannot simply remove D from L1 because the block of D is updated. So at that time, the block need to be written back here. So updated value will be written here, and then only you can delete D from here. So this is only required for dirty block in inclusive cache. But in inclusive cache, if you want to remove a updated block is same block is already there in L2, right? So you can delete it, and no need to write it back in L2 because the A is not dirty in L1. Since A is not dirty in L1, then the copy that is available in L1 and the copy that is available in L2, they are same. If they are same, then we will not write it back, we'll simply delete it from L1. So this is called inclusive cache. But in exclusive cache, what we are saying, if you go to exclusive cache, then there is a L1 cache, there is a L2 cache, okay. And what we are saying that whatever data available in L1, suppose A and D here, these two block will not be available in L2. In L2 maybe there will be some other block available, but not A and D. Why we go for this design? Because in this way we can store more block in cache. Consider the entire thing is cache. Entire thing is cache. So in inclusive, we are using two space for A, two space for D, which is not required, right? If the block is in cache, that is fine. Maybe searching or managing, we need another advanced technique, but that is different thing. But if the block is here, it is fine. But now the concept here is, the problem here is, if you want to remove any of the blocks, suppose A is not dirty, D is dirty again, and you are removing A from the LLC. In that case also, you have to write it back in L2. Why? Because if you simply remove the block, it means that the block will be vanished from the cache. The block is vanished from the cache. That is not the thing, right? If there is a core here, C1 requested for the block, it may be possible that after some time another core C2 will also request for this block, or maybe the same core will request for this block. That's why you go with multi-level cache, right? Otherwise to एक level cache से हो जाता, right? Why you are going with L1, L2, even with single core? That's because the L1 is small, this L2 is big. So if there is a miss possible in A, then the block will be available here in A. So if there is a miss in L1, then L2 will give a support to us, right? Because L2 is bigger. So it means that the main property of cache will be violated if we simply remove the A here. So if it is exclusive cache, so it's no matter if it's a dirty or non-dirty or a clean block, if you are removing it from L1, you have to write it back here. This is called exclusive cache. Now this is the problem with NBM. In NBM, number of write is expensive, and here you are going for more number of writes, because in STTRAM, if you go for the left side design, here you are only writing the dirty block back to LLC. But here in this design, in right side design, you are writing all the blocks from L1 to LLC. So it means that it will congest the read queue more of LLC. So that's why exclusive cache is disadvantage in terms of STDRM based LLC. Is it clear now? Simple.
Yes, sir.
Okay. Any other doubt? Okay. If there are no doubts, then I'll stop here because it is already 10:05. So thank you for joining. We'll meet again tomorrow.